Hi, and welcome to TEMEKO. In this video, we will continue talking about the kinematic analysis. In the last lesson, we gave a good introduction to this analysis and mentioned the key characteristics a mechanism should have to be a good candidate for a kinematic analysis. Now let's talk about the final part of this analysis, the velocity and acceleration analysis, as well as how we could implement this in a computer program. By the end of this video, we expect you to have the complete information on how to confidently perform a full kinematic analysis on a kinematically driven mechanism. Let's jump into it. Let's start with the results of the position analysis. In the last lesson, we got the solution to our set of constraints represented as a vector of constraints, depending on the generalized coordinates and time. We focused on obtaining the values of the generalized coordinates that met this equality. We called this process a position analysis or coordinate analysis. Now, a velocity analysis will consist of finding the acting value of the generalized velocities for the mechanism configuration under study. If we take the vector of constraints and derive it, we'll get CQ times Q dot plus CT equals 0. Remember, this vector depends on the generalized coordinates and time. Again, we get a familiar term such as the Jacobian matrix of the constraints, but we also get the vector Q dot, which represents the generalized velocities, the term we are looking for. Now, maintaining the assumption that our Jacobian matrix is square and invertible, we can find the generalized velocities. Q dot equals minus CQ inverse times CT. And that is it. This will give us the vector of generalized velocities, which corresponds to the current mechanism configuration. Now, if I tell you about the acceleration analysis, you might automatically think, okay, it's all about finding the value of the generalized accelerations. And yes, you are right. How? Let's take the derivative of the results we used in our velocity analysis. Differentiating this expression results in delta Q, CQ times Q dot plus CT times Q dot plus delta T, CQ times Q dot plus CT equals 0. Working further on it, we will have CQ times Q double dot plus delta Q, CQ times Q dot plus 2 times delta T, CQ times Q dot plus delta T, CT equals 0. We can now solve for the vector of generalized accelerations. Q double dot equals CQ inverse times minus delta Q, CQ times Q dot minus 2 times delta T, CQ times Q dot minus delta T, CT. To make it simpler to read, we will call this expression as QC. Then we can write everything as Q double dot equals CQ inverse times QC. In this lesson, we complemented the kinematic analysis with the velocity and acceleration analysis. I think we are ready to do an example of the application of this analysis to a planar mechanism in the next video. Thanks for watching and see you soon.